heard the word inverse before? Yeah. Okay. So what are some things that like inverse means to you? Opposite. Okay. Can you be more specific about opposite?
Cancel each other out.
Oh yes, they cancel each other out. Okay, so can you give me an example of some opposites canceling each other out, Kaylee? Yes, I love that. Okay, so she is talking about inverse operation for multiplication. I would have like finished that with what's the inverse of multiplication? Division. What's the inverse of addition?
Subtraction.
Subtraction. What's the inverse of squaring something? Square rooting it. So now we're seeing like why we might be talking about inverses right now. Okay. So inverses are functions usually that undo each other. Although we'll talk about tomorrow, you can sometimes have inverse functions and sometimes you can have inverses that are not functions. So we'll go more into depth with that tomorrow. But we want to talk about this fact. So the inverses are functions that undo each other. And generally, like if there were one thing I would want you to take to your teachers next year in Algebra 3 or Honors Pre-Calculus, whatever you're taking, when I see my Honors Pre-Calculus students and I say, okay, what do you guys know about inverses? I want them to answer number 1, switch X and Y. That is something you should know about inverses going forward if we're talking about functions, things in terms of variables, X and Y. That's how you find inverses. Whether you're working with equations, whether you're working with graphs, whether you're working with tables, it doesn't matter, you switch X and Y. Now, if it's an equation, you'll go through and then solve for Y. Because don't we always like our equations to be Y equals generally? Generally, yeah. Probably the one exception we had so far has been the circle, x squared plus y squared equals r squared. We leave it alone. Now, if you switch x and y, remember x is always your domain and y is always your range. Well, if you switch the x's and the y's, then the domain and range also switch. Okay, so domain and range are switched. And visually, what you're going to see is your graph has been reflected over the line y equals x. Now, there are some questions in the book on the homework assignment that ask you to graph the inverse and the original function. And I put on the gold sheet that you don't have to do the graphs. Okay. So if you're interested in looking at the graphs, feel free to graph them on your own. Or if you want to use that Desmos app or the Desmos online, and you just want to type them in and see if that's true, you can do that. So if you want to make the connection visually for inverses, go ahead and graph it somewhere, okay, so that you can see what we're talking about. Okay. Now, on this slide, I'm just going to talk about 2 really basic examples. We're going to do an inverse on a graph and an inverse in a table. Okay. But the majority of the time, I'm going to be asking you about inverses as equations. Okay, but still, it doesn't matter. I could ask you about a graph. I can ask you about a table. What's the one thing you need to remember about inverses? X and Y switch. Okay. Okay. So it really wouldn't matter whatever line you wanted to draw. I have a line drawn here. It's a red line. It's a little bit hard to see. Let me see if I can make this a little bit bigger. Okay, we'll make this a little bit bigger, easier to see. Okay, so if you want to draw the exact same line that I have, and it doesn't necessarily have to be, I'm going to say it looks like I have a point at, this is -2, -6. Also looks like I have a point right here at like 4, 4. It almost looks like I had a point at 0, -2, but I think it's actually lower. So those look like my only 2 really nice points on my line. Okay, if you want to draw that same line. Okay, if you wanted to draw or like sketch a graph of the inverse, what I would recommend doing is, just like I've done for this line in particular, I picked out some ordered pairs that I could see. And then, like Kaylee said, do what to find an inverse? Switch x and y. So if -2, -6 is on the original graph, what point should be on the graph of the inverse? -6, -2. So I'm going to go 6 to the left and 2 up. Oh, sorry. Not 6 to the left and 2 up, 6 to the left and 2 down, right? Okay, so I'll mark this point as -6, -2. So signs don't change. The only thing that changes is the position of x and y. I flip-flopped them. If 4 is on the graph of my original, what's on the graph of my inverse? Also 4. Okay. So they share that point. And notice that point is on this dotted line. This dotted line is marked as y equals x, and that's the line of reflection, right? So if there's a point on the line of reflection, it doesn't really reflect. It's on both graphs. Now, if I draw my blue line at this point, I get something like that. And do you see how if I were to fold on that dotted line, the line that is y equals x, the red line would map onto the blue line and vice versa? Or map onto each other? So using your reflection knowledge from geometry. So that's what happens when you take points and you just flip-flop their x's and y's. It doesn't matter what the shape is. If it's not a line, it's always going to just be a reflection over the line y equals x. If it was the inverse in a table, so this is like some function, and I have x and y listed out, how would I make the inverse? Abby says? You just flip them, right? Soon we'll all be answering it, not just one person at a time. Soon we'll all just say, switch x and y. Okay, excellent. So let's do that. Here's our inverse. X, y. I'm going to take all of these y's, -1, 1, 3, 5, 7. And then I'm going to switch all of my x's to be my new y's. So that's going to be -2, -1, 0, 1, and 2.
Boom.
If I took the time to graph those on a coordinate plane, they would be reflections in the line y equals x. It looks like I am graphing a line right there. Okay, it has a slope of 2, a y-intercept of 3, so the line y equals 2x plus 3. Okay, now let's do one with an equation. F of x equals 1/3 x minus 2. So if you're being asked to find the inverse, what would you do? Switch x and y. Now the one thing you have to be careful of in an equation is you might be tempted to also switch coefficients, but you don't. The only thing you switch is x and y. So if it would help you, anytime the book gives you f of x, you can write y instead. So I'll rewrite this because it's my notes, so I want to be clear about where everything's coming from. And then once I see that I have an equation in x and y, I just write x where I see y. So this is going to be an x. And I'm going to have a 1/3. Instead of x, it's going to be y minus 2. Okay. So don't be tempted to bring the 1/3 over with the x. It's not x. Something totally different. Okay, well, we don't want to just leave our answer like that. We want to go ahead and solve for y. So can you tell me the 2 steps I'm going to need to do to solve for y in this equation? Add 2, multiply by 3. So let's do that. We're going to get x plus 2 equals 1/3 y. And I'm just going to put the whole equation in parentheses and say like multiply by 3. You have to be really careful here On this side with the x plus 2, that 3 goes to both terms, right? It distributes to the 1/3 y, it distributes to the 2, it distributes to the x. So we're going to get y equals 3x plus 6. And I'll move this up so you can see it a little better. Gotta get rid of this screen shade. Now, there's a couple of different things that you can do here. Okay, you can mark it as y equals 3x plus 6, and I know that you're finding an inverse. Note that the book may use some notation for inverses, and sometimes you see it as like y to the -1, or this is really f inverse x. So when you put the -1, it just means inverse. So this would be y inverse or f inverse. 3x plus 6. And I just say that f inverse. So the one thing we don't want to do is label it f of x because it's not the original function. It's the inverse function. Okay? You could also label it g of x if you wanted to. That would be fine. Okay. You try this one for me. F of x equals 2x plus 3. See if you can get the inverse function for me. Remember, step 1 is to switch x and y. So in this example, I didn't rewrite it again as y equals. I know f of x is y. But I probably wouldn't want to switch like f and f of x. That gets confusing. So if you see it in function notation, change it to y's. And then I see most people are subtracting 3. Excellent. So we're using inverse operations, opposite operations. And now how are you going to get y all by itself? You can divide by 2. I would also call that multiplying by 1/2. And that's going to distribute to everything. So my f inverse of x is going to be 1/2 x minus 3/2. Now, if you wrote it as f inverse of x equals x minus 3 over 2, that's okay. That is the same thing, as long as x minus 3 is all over 2. Okay. I like to write mine in the form 1/2 x minus 3/2, just because if I were really going to graph them, then it's in slope-intercept form. And that's an easy thing for me to do. Any questions or concerns? Okay. One more thing that we want to talk about before we leave today, because tomorrow we need to know. In order to verify two functions are inverse, you verify two functions are inverses by doing compositions. So remember yesterday I introduced this compositions notation with the open circle. If you prefer to use parentheses, feel free to go ahead and do that. You should just be able to recognize both because either one could appear on a quiz or a test. Now the one thing my students always dislike about verifying inverses, although usually fairly simple, is that technically you have to do both versions. You have to show that f of g is equal to x and g of f is also equal to x. Because compositions, unlike addition and multiplication, are not commutative. They're not always the same both ways. So that's the one bummer about it. But the good part about it is, if they are inverses, your work is really easy. And if they aren't inverses, you'll be able to tell pretty quickly. Okay? So you've got to do both. And what you need to show in both compositions is that both compositions totally undo all of the numbers, and the only thing that's left is x. If it was equal to 2x, not an inverse. If it's equal to x minus 1, not an inverse. If it's equal to 1, not an inverse. And the only way it's equal to an inverse is if it's equal to x. So we'll do an example. Over is not helpful. Okay, so let's verify f of x equals 2x plus 4 and g of x equals x minus 4 over 2 are inverses of each other. Okay, when asked to do verification, you're just running through two compositions. So I'm going to start with f of g. So I'm going to take g, x minus 4 over 2, and I'm going to plug it in for x right there. So that's going to be 2 times x minus 4 over 2 plus 4. Now, show me your steps. I care about your work. Okay. Show me how it simplifies. What's the first thing that simplifies? The 2's cancel first. I can't do the minus 4 and the plus 4 yet. Okay. In order of operations, what would you do first? Multiplication. 2 over 2, or 2 times 1/2, is going to cancel out, right? So we get x minus 4 plus 4, which then cancels to be x. Do you see it's not hard work? At least what have I confused you on? Order of operations? So
How does it equal? How does it cancel?
how does what cancel?
The 2.
That's like 2 over 1 times x minus 4 over 2. And I can cross cancel. A 2 in the numerator is going to cancel a 2 in the denominator. Okay.
You don't distribute the 2.
I could distribute the 2 and get 2x minus 8 divided by 2 and then divide each of them by 2 and get x minus 4, but that seems like a lot more work than canceling.
Okay, I see where
Okay.
Or smarter.
All right.
I distributed.
All right. So let's go. G of f. Okay. My one answer to this whole like distribution question is it's not wrong in that case to distribute. You can distribute to x minus 4 because there's like no exponent on x minus 4. So you're allowed to distribute the multiplication. However, this whole idea about inverses is that they're going to undo each other, right? So rather than do it, distribute, and then undo it, divide, why not just undo it by canceling it out? That's my 2 cents about it. Okay, this time we're going to put f of x in for x in g of x. That's going to go into that x in the numerator. That's going to look like 2x plus 4 minus 4 all over 2. What would reduce first?
Fours cancel.
The
2x
4's
over 2.
would actually probably, I would say, would be the easiest thing to cancel first. They're all in the numerator, right? Plus 4 minus 4 is
0.
0, so that's 2x over 2, and then
1x,
that's
which
x.
is just x. Boom.
Yeah, so they're inverses. If you want to divide by 2 right away, I say that's okay, but in your work, if you divided by 2, it would become x plus 2 minus 2. It wouldn't be x plus 4 minus 4. because you'd have to divide all of them by 2. Does that make sense? Have you done this before? Oh, but it's kind of like proofs?
Yeah, because you're like trying to prove that they're like
Yeah.
Yeah.
Now, I'm going to be checking on quizzes and tests that you have these steps in between. So don't try and make any shortcuts. Don't be sad if you get points taken off because you didn't show your work. Ms. Cronky wants to see it. She's been very clear about that. She cares about your work, not your answer. Okay, you have a homework assignment in the textbook. For 13 through 19, you don't have to graph those, even though the book says, but that's the one where, like, if you're really interested in making this connection to when we find the inverse, what does that mean visually, graphically, go ahead and use the Desmos or graph a quick sketch and see that the 2 lines are reflections over the line y equals x. Tomorrow we're going to take it one step further. We're going to do inverses for different kinds of functions, nonlinear functions. So it gets a little bit tricky with some of our even roots. And so that's what we're going to talk about tomorrow.